Hello, my name is William Appleby, and today we are going to be determining an experimental value for the acceleration due to gravity on an object. This is part of a larger series, which is going to be determining the exact time it takes a beach ball to fall to the ground, and a large factor in that equation is gravity. If you haven't watched the first video explaining all the different variables that affect this, I would highly recommend going to watch that now and then come back to this. So for this video, we're just going to be focusing on gravity without using any other variables or constants. So for this, I went to my high school lab and conducted an experiment using simple harmonic motion of a spring oscillator. So I'll show the lab setup here. It's basically just a spring that's hanging with a mass on the bottom of it, and the mass actually doesn't matter, and I'll explain why that is in a second. It oscillates up and down, and I'll measure the displacement distance of the spring from equilibrium and a bunch of other stuff. And I'll explain why all this is relevant in this video and how we can determine a value for gravity. So let's get into it. Okay, so now that you've seen the lab setup, let me explain how springs and simple harmonic motion can actually connect back to gravity. So for any spring, let's say that this spring is attached to a cube. The mass doesn't really matter. Let's say it has mass m. And let's say it's not at its equilibrium position. Let's say the spring would want to be right here. And you know from personal experience that if you stretch a spring one way, it's going to want to go back the other way. So this is the same case here. In this distance that the string is displaced, which we're going to call delta x because it's the change in position, which is represented by x, from its equilibrium position here to where it actually is sitting here. And this spring is going to apply a force on this mass because it is away from its equilibrium position. And this force that this spring applies, we're going to call Fs for force of spring. And from this example, we know that it is proportional to the opposite of position because, or change in position, sorry. Because when you stretch it to the left, so let's say that this delta x is negative because it's going to the left, the force applied is to the right. So that means if it's negative delta x, the force would be positive, which means it's proportional to the inverse of delta x. But this is not the same for all springs because different springs made out of different material and different coil lengths and stuff like that can affect the amount of force that it gives over a certain distance. And to account for that, we use a constant called the spring constant. So the force of the spring is equal to negative k, which is the spring constant, times delta x. So this is a very basic physics equation that explains the force from any spring. In this lab, we can easily measure the delta x to get the force of the spring, which is important for determining gravity. But we do not have this k value. So we need to determine the k value for this specific spring. So now we need to figure out how simple harmonic motion can help us find the value of k. So let's take a step back for a second and think about what simple harmonic motion actually is. Any simple harmonic oscillator follows the path of a cosine graph, which looks something like this. And this is as time goes on. This is the position of the object or whatever it is, which we can represent as x. So the equation for this would be x of t, so x, the position at time t, is equal to cosine of t. And this is just the trigonometric definition of cosine. But for our purposes, we're going to have to add in a couple other constants that have an effect on the simple harmonic motion. So in this case, x of t is going to be equal to a cosine omega t. So the a is just amplitude, which can affect how tall the peaks of the graph are, or the furthest displacement distance in the case that we have. And then w is going to be the angular speed, which we're actually going to take a look at Desmos in a second here. So I just plugged the first equation into Desmos, and as you can see, this is the graph that is simple harmonic motion. But if we add the constants that we were just talking about, let's see how each of these affects it. So a, like I said, is the amplitude, so the higher it gets, the higher the peaks will be. and then W is going to be the speed at which it occurs. So let's go ahead and mark 2 pi on this graph, because 2 pi radians is how long it takes a simple cosine graph to make one full oscillation. So if this was the hanging mass, this would be its position at the top, displaced from equilibrium, and then it makes its way all the way to the bottom and then back to the top. That would be one full rotation is at 2 pi. But when we adjust the angular speed, you can see it gets faster and faster. So if the angular speed was 4, instead of one rotation in 2 pi radians, it would be 1, 2, 3, 4 rotations. So that's the effect that this WT has on this graph, and I'll explain more on why that matters in a second. So before we move on from Desmos, I want to talk about one new variable, which is uppercase T, which is period. So the period of a graph is how long it takes to make one full rotation. So it's like going from this first point to this second peak. So the period for this graph would be pi over 2, because it goes from 0 to pi over 2 in one full rotation. And this will be useful in a second. So going back to this W variable I introduced earlier that I said was the speed can just be written as 2 pi over the period. And this is because usually it would be 2 pi radians for one full rotation like it is here. But when you start increasing W, the period decreases, so that you can see this inverse relationship right here. And so you can see that if you were to plug in 2 pi for the period, which is the period of a normal cosine graph, you would just get W is equal to 1. So that makes sense, because it would just be cosine of T in that case. But then once you start decreasing the period, so say it was just pi, the W would be 2. And the units for W are radians per second, because this is 2 pi radians and the period is in seconds. So I'm going to be honest, we don't really care about the position of this hanging mass. We would rather know the acceleration of the hanging mass. So the acceleration is going to be equal to the second derivative of the position, because the derivative is the rate of change of position is velocity, and the rate of change of velocity is acceleration. So we're going to need to derive this equation twice. So let's start by using the chain rule, which I'll write out real quick. Okay, so this is the chain rule. It says that the derivative of any function that has another function inside of it is equal to the derivative of the first function with the second function inside of it times the derivative of the second function. So in this case, a cosine omega t is a composite function, so it has something inside of this cosine. So f in this case is going to be equal to a cosine u, and we'll let u equal wt, or omega t. And the derivative of this would just be negative a sine u, and this is because the derivative of cosine is sine. So now we just need to multiply this by the derivative of g of x, and g is going to be omega times t. So that means that the derivative of g will just be w, or omega, because we're deriving with respect to t. So if we multiply this times omega, then that gives us with the derivative, which is going to be velocity, is equal to negative a sine omega t, replacing that u, times w, which we can rewrite as negative w a sine wt. So that is going to be our velocity expression, but we're going to need to take the derivative again to get to acceleration. So we're going to need to do the same thing using the chain rule. F is going to be equal to negative w a sine u, and u is going to be equal to wt again. So that means that the derivative of f is going to be negative w a cosine u, and that's because the derivative of negative sine is negative cosine. And then we're still going to have to multiply this by g, and g is equal to wt. So that means that the derivative of g is still equal to w. So multiplying this, we get our acceleration with respect to time is equal to negative w squared, because we multiplied that w again, a cosine and then we'll replace the u with wt. We can actually simplify this expression though, because this a cosine wt is the same as the a cosine wt that was the original delta x expression up here. So we can replace this a cosine wt with this one, meaning it's just x of t. So now we can write a of t as being negative w squared times x of t. And now we can drop the t notation and just say that acceleration is equal to negative w squared x, or delta x in this case, because that matches the notation we used up here at the top. And it's the same x because it's the displacement from equilibrium. So now let's talk about how this w fits in with what we did at the beginning, which is f of s is equal to negative k delta x. So we can replace fs for ma. So ma is equal to negative k delta x, and that's just using Newton's second law. So the acceleration of any spring system will just be equal to negative k delta x over m. And we know that this acceleration is going to be the same as this acceleration because the spring is going to be in simple harmonic motion. So we can say that negative k over m delta x, which is this first part down here, is equal to negative w squared delta x, which is the second part down here. And now we can see that these delta x's will cancel on both sides, leading to the fact that negative k over m is equal to negative w squared, or just w squared is equal to k over m because the negatives cancel on both sides. If you remember earlier, we said that w is equal to 2 pi over t because it's the speed of a harmonic motion. So if w squared is equal to k over m and w is equal to 2 pi over t, we can rewrite this w as w squared by squaring both sides. So w squared is equal to 2 pi over t squared. So then we can set this w squared and this w squared equal to each other by saying that k over m is equal to 2 pi over t squared. So now we can finally solve for k, which is what we were trying to get to this entire time. So by distributing the square to the top and bottom of this fraction, we get that 4 pi squared over t squared times m is equal to k. So we finally have an expression for k. So now if we think about the situation of the spring that we had in the lab, it is not horizontal like how we drew earlier, it's actually going to be vertical. So with this vertical spring, this force of weight is going to be mg. So instead of the ma that we used here setting equal to this, we can use mg. So mg is going to be equal to negative k delta x. And using our new equation that we have for k, we can plug into this equation. mg is equal to negative 4 pi squared m over t squared times delta x. And then we can divide by mass on both sides to get gravity. So gravity is going to be negative 4 pi squared delta x over t squared. So now we finally have a full equation to solve for gravity from the data we collected in this lab. But there is a question that arises. So the period is what we're going to be measuring in the lab, is how long it takes for one complete oscillation of the simple harmonic motion. The 4 pi squared is just going to be a constant, but the delta x is confusing because I said earlier that it's the distance from equilibrium. So in this case, I measured the unstretched length of the spring, and then I measured the length that it was stretched with the mass that we had put on it. And delta x is just equal to final position minus initial position. So plugging in these two values, we get that delta x is equal to around 5.55 centimeters. which is going to be about 0.0555 meters. So now we should have everything we need to solve for gravity. So what you're seeing now are the 5 best trials that I conducted during this lab. By best trial, I just mean that it had the least amount of horizontal movement because the goal was for perfect vertical oscillations and no horizontal movement. I did a bunch of different trials, and these are just the 5 I thought were the best. What you're actually seeing is the timer starts when it hits the top of an oscillation, and then the timer goes for 20 oscillations before stopping. And the reason for that is if we just timed one oscillation, which is what t is going to be and what the period is going to be, it would not be very accurate because one oscillation can have a lot of human error or just other sources of error. So we do 20 oscillations, and then when we're averaging all of these numbers, we're going to divide each one by 20 to get the actual period because the number on screen is just 20 periods. So the average time was 0.5456. Okay, so now that we've done the lab, we know that the period of this spring is going to be about half a second. And so with this information, we should be able to solve for gravity. So if we plug into this equation up here with these numbers, we'll get gravity is equal to negative 4 pi squared times 0.0555 over 0.5456 squared. We get that gravity is equal to negative 7.36 meters per second squared. But that is not very close to the actual value, which is negative 9.8 meters per second squared. And the way we account for this error is actually going to be the mass of the spring itself. So we canceled out the masses of the hanging mass earlier, but we're actually going to need to use the mass of the hanging mass, which is 50 grams or 0.05 kilograms. That's going to be important because if we take into account the mass of the spring, which I measured while I was in the lab, it was also 50 grams, or it was like 49.9, but I'm rounding to 50, which is also 0.05 kilograms. So why is this important? Basically, when we were calculating using this mass the entire time in a bunch of different equations, we weren't accounting for the mass of the spring, which also is being pulled by gravity and accelerated by gravity that changes the oscillation of the spring. But the thing is, with a hanging mass, or with a hanging spring that looks like this, the mass at the top is being stretched and pulled less than the mass at the bottom. So the way we account for this is the moment of inertia of the spring. And for like a rod that's fixed at one end, which is kind of the same situation we have here, it's going to be 1/3 of the mass. So 1/3 of the entire mass of the spring is going to be affected by gravity the same way the hanging mass is. So if this doesn't make sense, a way you can think about it is the equilibrium position of the spring looks something like this, and then the stretched position of the spring looks something like this. So as you go further down on this spring, this coil is much more displaced from its equilibrium position than a coil near the top would be. So that displacement is what we're talking about when we say 1/3 of the mass is the effective mass being pulled by gravity. So that's why that's the part of the mass that we use in the calculations I'm about to show. So when we solved for K earlier right here, we were just using the mass of just the hanging mass, and now we're going to have to add on 1/3 of the mass of the spring because that is also being weighed down into gravity and has an effect on the spring constant. So we can say that K is just equal to 4 pi squared over T squared times M plus 1/3 ms. And then we brought that over here to solve for gravity. And to do that, we used mg is equal to negative k delta x, and then we divided both sides by mass. So we ended up being able to cancel out the masses, but in this case we aren't going to be able to cancel out the masses. So I'm going to rewrite it from this step here.
So mg is equal to negative 4 pi squared times mass plus 1/3 mass of spring over t squared times delta x.
So now when we divide by mass, it's just going to go into the denominator. And this will allow us to rewrite our gravity equation
As 4 pi squared times m plus 1/3 mass of spring times delta x over t squared m.
So now that we have this, we can plug in all of our numbers, and I'll pull up the calculation in Desmos really quick. So as you can see, when we plug this into Desmos, we get a value of g that is about 9.81. And this value of gravity is extremely close to the actual value. In fact, the first 3 decimal places are exactly right, and that would be meters per second squared. So that basically shows that this lab was very successful, and there were very few sources of error in this lab, and we accounted for pretty much everything that could have happened with the spring, and we got a very realistic value. The only thing that we didn't account for in this lab was the dampening of the spring, because as time goes on in any spring motion, the amplitude of the motion actually decreases, but this is very hard to observe in situations like we had where we were using a very light mass, because this effect would be very minimal and would have almost no effect on the actual motion of the spring, especially since we only timed 20 oscillations at a time. It had almost zero effect, which is the reason why I didn't choose to include the equations for that. But overall, we got a very nice looking answer here, and this is the gravity value that we will use for the rest of the series for finding the time it takes the beach ball to hit the ground when released from rest in free fall. And yeah, that leaves a couple other variables we have to solve for. I hope you enjoyed watching this, and I hope you learned something. I'll see you in the next episode.